Hey science fans, worry not, no singing today. So we're going to be looking at orbital motion. So orbit means circling around something, motion means movement. Let's get cracking. So here's three objects. We've got a moon, we've got a car drifting, and we have got a merry-go-round type ride. This motion requires a force in order to change direction. What provides the force in each of the examples? So let's have a think about those. So we've got the moon, we've got gravity holding the moon in position. The moon is Earth's natural satellite, and it is moving around the Earth as the Earth orbits the sun. And then we've got the driving force from the acceleration from the engine moving that car to change its direction. And then we've got a couple of forces happening here, but we've got gravity and acceleration working together on the motion here. And you might have heard of centripetal force, centrifugal force, and we're going to be looking at those forces today. Okay, to get a grade 4, you need to this all sort of very similar to the last ones. This is just about how objects orbit one another, and it sort of links in with the Big Bang, and it links in with the model of the universe. Is this a satellite? Yes, it is. Is this a satellite? Yes, it is. This was the first satellite. This is. And is this a satellite? Yes, it is. It's the International Space Station. Is this a satellite? Yes, it is. So what is a satellite? Please note the spelling of the word satellite. I always spell it wrong. 1 T, 2 L's, 1 T. Is this a satellite? Well, in theory, because it orbits. Is this a satellite? We're not orbiting one particular point, but yes, we are, because we're coming from this particular point of the Big Bang. So yes, they're all satellites. So a satellite is something that orbits something else. So the moon is a natural satellite, and the Earth is a natural satellite of the sun, and the communication satellites orbit the Earth, and so they're artificial satellites. They're small objects moving around a larger object due to gravity. I'd jot that down. Gravity provides the force that keeps the satellites in their circular orbit. They're both natural and man-made satellites. Can you think of two examples of each? Well, we just did those. So the Earth and the Moon are natural satellites. You know, the asteroids are natural. Excuse me, I'm going to sneeze. No, we're all right. And then man-made satellites, we have geographical and communication satellites as well as space stations. There's some really good examples. The moon, the Earth, Halley's Comet, that's a good one. And Titan is an example of a moon of Saturn. Sputnik is probably the most famous satellite because it was the first ever artificial satellite in space. Navstar 1 was the first GPS satellite. Obviously, there are loads of those now. Hubble Telescope and the ISS, the habitable satellite, the International Space Station. Okay, so what we're going to do is we're going to try this question. Give one difference and one similarity between a planet and a natural satellite. So this is called a compare question, which is a command word from the exams that people don't tend to do too well on, but it literally means give a difference and a similarity between a planet and a natural satellite. So the similarity, I'm just going to write sim on here instead. The similarity is that they both orbit, I'm going to say celestial bodies, so something in space. Okay, they both orbit celestial bodies. What else do I know about them? See if I can think of another one. They do not emit light. That's a good one. I've got the answers on the next slide, but I just want to show you how my brain works. Because you must give a similarity and a difference. A difference between a planet and a natural satellite. So planets orbit stars in a solar system, whereas natural satellites, and you should always put whereas and name what you're talking about, whereas natural satellites are smaller and they tend to orbit planets. Give one difference and one similarity between a natural satellite and an artificial satellite. Oh, sorry, I flipped forward the slide there. That was annoying. Let's quickly go through the answers, though. So both planets and natural satellite orbit a large celestial body. Boom. Neither emits light. Yes. Planets are always natural and always orbit a star. I said they orbit stars, and then natural satellites planets are always natural satellites and always orbit. Yeah, and satellites have smaller masses. I said they were smaller. I didn't say this, that they could be artificial and orbit non-stellar bodies, so not stars. Okay, so I've also skipped forward on the other question, which is very annoying, but let's talk about how we would, so this again is a comparison. So they both orbit a celestial body. I think that's meant to say celestial body. Natural satellite are ones that have formed naturally, such as the moon, tick. So this is their difference. Artificial satellites are man-made, tick, and often solar powered. They're placed in orbit by us, and usually they communicate with Earth. So it's quite easy to pick up similarity and differences, but you must compare them. So you must say whereas, although, make sure you use the names of them. So if you say some satellites are natural and some satellites aren't, you haven't identified which ones are and which ones aren't. So you need to be really clear on the names. Why are astronauts weightless? I'm making some really weird noises today. I must be tired. So just remembering that weight is mass. Oops, what have I done there? Is mass times gravitational field strength. Don't know where my mass has gone. So on Earth, if I weighed 100 kilograms and I multiply, if my mass was 100 kilograms and the gravitational field strength is 10, we know it's like 9.8 something. That would mean I would have a weight on Earth of 1,000 newtons. I know we use weight and we talk about stones and kilograms when we talk about weight, but weight really is a measurement of the force that you place on an object. So yeah, it's a contact force. So why are astronauts weightless? Well, you might think like, oh, okay, well, there's no gravity where they are. So if you're multiplying that by 0, then that would make 100 times 0 is 0. But actually, astronauts are constantly falling to Earth. So they're not completely weightless. I just want to talk to you about this. So I don't actually remember much about the episode, but in The Simpsons, when Homer goes to space, I know The Simpsons are on, I think they're on like Disney Plus or something. This is one of my favourite bits of television ever, because he opens a bag of crisps in the rocket and spaceship or whatever you want to call it. And it's just a lovely bit of TV where he goes and instead of trying to collect them, he eats them by going do 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 do. And it's just the most delightful sound effects. I love it. Oh, look. Okay. So we're going to talk about how and why things orbit. And this is really what Newton became not famous for. So Newton's apple idea, that he got the idea of gravity of it falling, it didn't stop there. Newton kind of got the idea of the fact that if he threw an apple, why does it not carry on going around the Earth? So let's think about this watermelon. If I gave it a medium kick, the gravity would mean that it would plummet to the, plummet, it's on a small table. That says, how far can you kick a dog? Do not kick dogs. Watermelons, fine. So gravity means that it's going to go down to Earth. If I give it a harder kick, what do I know about that? And this is what he was thinking about with his apple. If I throw an apple, if I throw it harder, it's going to go further, but gravity is still going to mean that it hits the ground. Just means it goes further. What if I shoot it with a cannon? Well, it's going to go even further, but it will hit the ground. Okay. What if I get an even bigger cannon? It's going to go further, but it's still going to hit the ground. How about if I got a cannon so large, I could put this watermelon around the Earth? Would it keep going? Would it crash into the Earth? Yes. What if it was even bigger? If we had enough force, I don't know why it says dog, like I obviously did this originally with a dog and then changed it to a watermelon. If I had the world's biggest cannon and I could get that watermelon into orbit, assuming there was no air resistance, so it's got to get through atmosphere, blah, 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 it would, in theory, orbit the Earth because it would have equal amounts of acceleration and gravity. So the watermelon is falling towards Earth, but it never hits the Earth. It's still orbiting. Why is that? So the force that keeps the object moving in a circle is called the centripetal force. You probably heard that when we talk about roller coasters and swinging buckets round. So as the object is going round, it is constantly falling, and gravity is what's keeping it in check. So we need to look at why it's not actually falling. This is centripetal force and circular motion. So when we look at Newton's first law, we're talking about changing velocity. If the direction changes, but if the velocity changes, then the object is accelerating, which requires a force. So if this object might have a constant speed moving around in a direction, so the speed's the same, but as soon as it changes direction, it changes velocity. And as we know, so velocity is distance divided by time. So velocity means that it's changing direction. Speed, it can be going the same distance in the same time, and the speed is kept the same, but because it's changing direction, this changes. Okay, and remember that acceleration is change in velocity divided by time, which means that if the velocity is changing, our object is constantly accelerating. Okay, so that force is driving the object around the Earth at the same time that the gravity is pulling it downwards. So the speed is the same, but the velocity and acceleration is changing because the direction is changing. Okay, centripetal force acts because gravity is acting inwards, but the satellite is accelerating towards the centre. So at right angles to the motion, it doesn't affect the speed, just the direction. So the object is accelerating downwards but speeding forwards. Centripetal force. So this is the question that we've just answered, really. How can it be accelerating, have a change in velocity, be at a constant speed? So again, speed is distance divided by time, which is the same as velocity, which is distance divided by time. But velocity means it's changing direction. And therefore, if the direction is changing, the velocity is changing, which means therefore the acceleration is changing because that's a change in velocity divided by time. So therefore, if it changes direction, it's changing acceleration. Speed is scalar, so direction doesn't matter. Velocity is a vector, so direction does matter. As acceleration is a change in velocity divided by time, as the velocity changes, the object is always accelerating. Okay, here is a 6-mark question. I suggest you pause it and see how many of these you can get right. So it says, on figure 1, now a lot of people miss these marks, and I always say hump for the marks. So this is a grade 7 to 9. On figure 1, draw arrows indicating the direction of the planet's acceleration and the direction of the planet's velocity, and then explain why the acceleration changes. Pause it. Right, let's go through the answers. Okay, so on your diagram, you should have had acceleration, velocity. This means that's the acceleration acts along the radius of the orbit towards the centre. This means it acts at right angles to velocity. So that's the first 2 marks. Boom, boom. So this is basically a description for 6 marks. So the speed is not changed, 1 mark. Velocity is vector, good. The acceleration causes the planet to move in a circular pathway, experiences changing velocity, but not a changing speed. Satellite A is orbiting faster than satellite B. Boom. That one wasn't on there, was it? I'll double check that. So have a go, see whether you got any of those right. Okay, so let's go back to our initial examples. These are the 3 objects that we had that were doing orbital motion. Let's think of 3 factors that will affect the size of the force required. So remember, this is the force of acceleration, or I don't know why I drew it that way, the force of acceleration and gravity and velocity moving here. What is going to affect those? What's going to affect the size of the force? Well, we know force is mass times acceleration. So we need to think about the mass of the object, the speed of the object, or how the object is changing, and the force of gravity as well. There's a lot of answers to this, really. Like you could have, for here, we could have the weight or the mass of the people, will depend upon how they spin around. We already know that this is an actual satellite, so it will be travelling at speed and accelerating towards the Earth because of gravity. So artificial satellites are continually accelerating towards the Earth. So like we said, they're accelerating towards the Earth. So the motion of gravity means that they're accelerating towards the Earth. However, they are also travelling at speed. And this here is like tangible motion. So they're going in this direction. So as they change direction, their velocity changes. So they're continually accelerating because of the gravitational force of attraction between the satellite and the Earth. But the closer you are to Earth, the stronger the force is. The closer to Earth, the stronger the force is. So this also then can dictate how fast they need to be travelling to stop them crashing into the Earth. So the forward speed of a satellite must be just right to keep the satellite in orbit. If it's too slow, it will fall to Earth, which is what I just said. If the motion is too fast, out into space. Look at this as a fantastic picture of the Earth with different satellites. Can you see there's like a high density of satellites here, and then there's quite a high density in this kind of ring type motion around there. We always get this view of Earth from a distance, but you don't actually think about how many satellites are now in orbit. Isn't that cool? Look at it. I mean, is it cool or is it not cool? I'm not sure. So these here on the further out you go, these are where we get geostationary satellites. Now, geo means Earth, stationary means still. So these satellites are orbiting at the same speed that the Earth rotates, so their position relative to us never changes. So this satellite will move with the rotation of the Earth. So this satellite, let's say it's over like, is that North America? Let's say it's over North America. It will always be over North America because it is travelling at the same speed as the Earth's rotation. Whereas the ones that are closer, and these tend to give sort of more, I don't know what word I was looking for there, but these tend to be the lower ones are the ones we use for weather because we can see the clouds moving in more detail. And they move around the Earth more quickly because they are closer to the Earth. They have to move quicker than the Earth's rotation because they're so close. And because they're so close, the gravity is stronger, therefore the speed that they need to be travelling needs to be greater to overcome the gravity. Okay, so the wider the orbit, the slower the satellite is going. Okay, so you can see this here, like Mercury is travelling at 48 kilometres per second, whereas Neptune has a speed of 5.3, so that's, considerably less because it is further away, so less gravity pulling it towards the sun, acting upon it, the gravity is weaker, and therefore a lower speed is required to keep it maintaining orbit. Are there any discrepancies? So a stable orbit is when the force of gravity is equal to the speed of the satellite. Okay. So to ensure it stays in a stable orbit, depending on where it is, the force of gravity needs to be equal to the, equal to the speed, yeah. If the speed increases, more force is going to be required. We can balance this out by increasing the radius of the orbit, and this decreases the speed. So you can decide how fast you want your orbit to travel by how far away it is from the centre. Just finally going to end with a gap fill about factors affecting centripetal force. So the smaller the radius of the circle, the centripetal force to keep the object moving. Well, that's going to need to be greater because it's going to be travelling at a greater speed. The faster an object is moving, the smaller the radius of the orbit. If the speed of an orbit is something, then the radius must also. Lovely. Boom. That is the final one of the space topic. We will obviously go over that in lessons, etc. Got plenty of time to. Thank you for those people who sent me Life Cycle of a Star. You are brilliant. If I don't, I've got one more lesson. I was going to do just a summary thing on Thursday, but other than that, that's going to be it for the year. Have a brilliant summer. Bye.